Okay, hi there. This is our Reverse Osmosis Part 2 board. More terminology and different aspects of RO units. First thing we'll mention is colloids. They're very small, 0.001 to 1 nanometer. They're very stable in water. They're good absorbers of free ions. If you shine light through a water sample, you'll see the beam in the water. That's colloids. They don't settle out. A lot of different ions can form them. They're very hard to get out of the water. We have the Langmuir saturation index. This determines if water is corrosive or scale forming. This is really important in water distribution systems. You want your water to plate a slight layer of calcium carbonate on the piping, but you didn't want it to scale, and you also didn't want to corrode the piping. There's a lot of good YouTube videos on how to determine this, but it is based on the pH, temperature, calcium hardness, alkalinity, total dissolved solids. These all come into play when the calcium carbonate starts dropping out of solution. The one that can be controlled easily is pH. Cooling towers, you'll drop the pH to change when the calcium drops out of solution. Also may form some calcium sulfates that do not form the hard scale layers. You'll find this in the back end of ROs. As you take out more permeate out of the water, you'll concentrate the hardness and alkalinity. You'll reach a point where you'll start forming scale. pH is really important. It determines a lot of the chemical reactions. This can also be very difficult to get an accurate measure on. You need high purity pH probes. Temperature will affect it quite a lot. This is really, the only time it's really important on ROs if you're adding sodium hydroxide to the second pass to get rid of carbon dioxide. Carbon dioxide is a gas, it will go through the membrane. You add sodium hydroxide and it'll form a carbonate which comes out of the water with the RO membrane. And you need to maintain about an 8.4 pH so you can strip all your CO2 out. Depends on what you're doing downstream with the water, but all the gases will go through an RO membrane. Another time this is really important if you're doing a clean in place. High and low pHs combined with high temperatures can destroy the polyester support on the membranes. But normal operation, the only time you're really going to worry about this if you're adding sodium hydroxide or if you're doing clean in place. The rest of your water should be pretty uniform. Silt density index, SDI. This is a measure of the colloids in the water. Basically, you run a sample through a 0.45 nanometer filter. You hold the pressure at 2 bars, 30 psi, gives you a uniform flow. You time the first 500 millimeter sample, and then you run the water for 15 minutes, and then you do another 500 millimeter sample timed. This goes into an equation and it gives you your SDI index. A lot of membrane manufacturers have specifications on what this should be. You can also take your filter and have it analyzed for what colloids are in the water. If the filter comes out black, it could be manganese. If it's orange, it could be iron. Gray could be sulfur. Tan, it could be organics and silt. So this can tell you kind of what's in your water. Where this is a problem, it can cause plugging in the RO itself. This video just starts with the water coming to the RO. We don't really talk much about pre-treatment. Your inlet water quality, you must know it before running design projections. It should be year-round. And if you change water throughout the year, if you go from a city to a well water, that can create a lot of problems with your ROs. City water, it may have excess coagulants, alum, ferric chloride, ferrous sulfate. The alum, the hydroxide can form aluminum silicates on your membranes. Your ferric compounds can form colloids, can plug them up. So basically you need to check the water, even if you're having a municipal or city water. It may have high SDI index also. So consider the city water an unknown source. Anytime you change water, you really need to know what is being changed. Well water can have hydrogen sulfide gas. It's not removed. Gases go through the membranes. If it's oxidized, it can drop out as sulfur, and that can form a pretty tenacious scale in the membranes. Iron and manganese, they can oxidize and form colloids. Normal iron out of the well will be taken out by the ROs, but once it gets oxidized, it changes states and it can scale and do a lot of damage to the membranes. Silica can form somewhere around 22 different species with stuff. Silica is really quite a problem. It can create some pretty hard scales. Some of the scales it forms can be pretty sharp and damage the membranes. Hydrocarbons, this is mostly for surface water. If you have diesel, any kind of hydrocarbons that end up in the water, it can destroy your support layer of the membrane. This is more susceptible. These layers get damaged and they compact, and then it drops down the permeate. One of your major problems with ROs is biofouling. Most of this other stuff can be dealt with design issues. With biofouling, when I first started, we used to use chlorine gas. Like I say, ammonia is annoying and chlorine gas is deadly. Then they went to a hypochlorite, which is a little safer. Nowadays you have chloramines, you're adding chlorine and ammonia. Chlorine dioxide, you're using rock salt through a generator to produce chlorine dioxide. You got ozone, ultraviolet, quite a few different biocides. The problem is they all have different damaging effects on the membranes. The chlorine itself is the worst. Chloramines, they have a lot higher tolerance. Chlorine dioxide, it's up in the air if they'll damage membranes or not. This is the big thing on RO membrane design. Having membranes that you can keep from biofouling and use less energy for producing water. As of right now, biofouling is a major problem. One of the things you run across, the microbes use carbon, total organic carbon or assimilable organic carbon. This is produced when you chlorinate water. The total organic carbon molecules break down into smaller molecules, which are food for the microbes. So you chlorinate, you kill all the stuff in the water, and what's left is more food for more microbes. You're actually disinfecting, you're not sterilizing the water, so there's possibly always something coming through. It doesn't take much to start quite a colony growing on your RO membrane. Your microbes, they need organic carbon, phosphate, nitrates. Some can be anaerobic. It's quite a mix of things that can happen. If you do not deal with the microbes or the organic growth on your membranes, you can get plugging around your mesh, and then scale form. There's no water, there's no cross velocity flow through here, so it will deposit scale. You can have colonies that basically the biocides can't reach. They have protection membranes, or dirt and stuff will form around them. You can get large colonies that slough off and go down and start growing further down the RO or plugging it up. This can be a really difficult thing to deal with. And that's why it's recommended every 24 hours to flush with RO water with a biocide. You have to use an approved biocide to minimize this. Membranes, you have colloidal cake. These are all your colloids. You have your iron, manganese, could be different hydroxides. They'll form layers, and then as they get compressed, they'll proceed to seal off the membrane. At first, they'll minimize the flow through the membrane. You may have higher ions going through the membrane with the permeate. This can be really hard to clean. Your clean in place will take care of a lot of this if you use the right chemicals. But doing a clean in place, you have to be careful. You can damage your membranes if you get your pH temperature off, wrong chemical, and it's just kind of hard on them. Your ROs, you need to use normalized differential pressure to do any real testing on them. If you run your test in the summer, and then you take the same data in the winter and don't compensate for the temperature and other items, your data will be skewed. Data will be wrong. Usually you want to start when you first put the membrane in service. New membranes, take all the data. That's your base point. If you change the concentrate flow, it'll affect this. Temperatures affect this. Water coming in will affect it. So you need basic operating parameters that are the same to get accurate data on these. You can correct for the temperatures and different things to get a more of an accurate baseline. You have your mesh or your feed spacer. The purpose of this is to maintain flow through the membrane. You want to maintain high velocity flow across the membrane surface, but not a lot of DP. These just float in there. So if you hit this thing with a lot of pressure for startup, you can shove all these down to the end of it, or it can move back and forth. And if you have scale, it can cut a hole in the membrane. This is very, very fine layer. Now you have the concentrate and water going through you. You'll have a degradation in your permeate. You can also have silt build up around these. You can have microbes build up around these and plug. So if you look at your DP across this, it'll tell you if you're plugging or scaling, have operation problems. If this gets too high, you have to do a clean in place and try to clean it up. These little things are the microbes. They'll accumulate back in here, and once they start growing, it's impossible to get rid of. And you're going to have microbes in systems. On scale, usually it's not a problem if your design is a good design. You get in problems if you change feed water or if you change the membranes. If you go to a membrane that has a higher water flux, you will starve the back element. Your cross flow velocity will be less. You're taking more water out in the front. Or if you adjust the concentrate flow trying to get higher permeate out of the system, you can create low cross flow velocity. You have your calcium goes up, magnesium, pH, alkalinity. This goes back to the Langelier formula to form scale. This can be difficult to clean up. The big thing before you change any membranes or elements in the RO system, you should run a design projection, see what it's going to do. Your cross flow velocity is critical. If you increase the flux in the beginning of your train, cross flow velocity could be lower on the back end, and concentration polarization goes up, so you get to the point where you start forming scale. If you have less permeate, you have lower quality. Basically, ions go through the membrane at a pretty uniform rate. Higher pressure, you push more water through, and that dilutes the ions, so you have better quality. So if you notice you have a higher DP, you got to run higher pressure to get the same permeate flow. Water quality starts falling off. You could be forming scales. You could be getting holes in the membranes. And you also have to consider too the water temperature. In the summer, you're going to have a little lower water quality with warmer water than the winter and colder water. If you have a uniform water temperature, then it's not really an issue. This pretty much concludes this part. I'm probably going to do 3 or 4 more of these. There's a lot more to talk about. This is just kind of some of the basic concept and ideas. The Langelier index, this is really important for any water systems. If you get it out of whack, you'll start corroding. You'll start either corroding stuff or you'll start scaling it up. Usually your silt density index, it'll stay the same throughout the year unless you change water quality. These are really important to know if you're going to do a design projection to determine what kind of element to use. They do have different spacer thicknesses, and you can have more membranes in the element. so you can get higher permeate flow per element, but you also run the risk of plugging more. If you go down to a smaller spacing here, you have a higher chance of plugging unless you have really clean water. Bigger spacing, you can deal with a little bit more colloids and silt. And that kind of concludes this one. Thank you.